Hello everyone, I'm Elham Mahamedi and I'm so pleased to present our paper on automating equipment productivity measurement using deep learning, which is conducted at Northumbria University. The co-authors of this paper are Dr. K. Rogage, Dr. Omar Doukari, and Professor Mohammed Kassem. In this presentation, I will give you an introduction to the research project, then I will talk about problem statement, research aims, and literature review. After that, I will explain the research methodology and the case study we did for testing and demonstration. And finally, I will present the conclusion of the research. In construction projects, site equipment represent a major cost element. Measuring equipment productivity helps to identify equipment efficiencies and improves their productivity. And we could say equipment productivity is a factor that affects the success of construction projects, particularly in equipment intensive projects like earthmoving and the tunnel project. In reality, in collecting the required data for equipment performance monitoring is time and resource consuming. Manual data collection is error-prone and impracticable in large projects. The recent advancement in the equipment technology can give us some useful information about different aspects of the equipment performance. But many companies still use the equipment that do not have such technologies and need to adopt other methods for monitoring their equipment performance. This demonstrates the need for automating the process of equipment data collection, measuring and benchmarking their productivity, and monitoring their performance in large construction projects. So the purpose of this paper is to propose a method for automating the collection of key data about equipment operations and the measurement of their productivity using low-cost smartphone sensors and deep learning techniques. In the literature, there are many methods that have been used for recognizing equipment activities and determining their activity duration and identifying their operation cycle time through automated data capture. And some researchers use RFID for tracking equipment activity, some use GPS for tracking equipment motion, and some studies use a vision-based method for monitoring equipment activity using photos and videos. Despite the contribution that these studies bring to monitoring construction equipment activity, there is still a lack of studies attempting to automate equipment productivity measurement. In our study, we contribute to this research domain by developing and testing a low-cost and simple-to-implement method for automating equipment productivity measurement with high accuracy using smartphone sensors. There are different metrics to measure equipment productivity. For example, some metric is based on downtime ratio, and the other metric is based on the percentage of time that an equipment unit is available for operation. By measuring such metrics for different types of equipment, we could produce productivity benchmarks and use them for project monitoring to identify underperforming equipment. So in this study, we explore the utilization ratio metric, and our main focus is identifying whether or not an equipment is working during the time that is available for use during the operation shift. Here I'd like to talk about our methodology. So in this study, we define two states for equipment: active or inactive. Active is the time that the equipment unit is actively working, and inactive is the time that the equipment unit is not working, including the idle time and the time the equipment engine is off. To classify the state as active and inactive, in the first step, we need to collect the required data. So we use the smartphone sensor data using a commercial application available on the phone. The application utilizes built-in smartphone sensors to capture IMU data, such as gyroscope, accelerometer, and linear acceleration, and the noise level. And also we use a camera to capture videos from equipment activities on the construction site to identify when the equipment unit is active or inactive as a ground truth. So the videos are used for labeling the timestamp sensor data and developing and validating machine learning models. The second step is data pre-processing. We identify sliding windows to divide input signal data into windows of signals. The size of each sliding window, which depends on the model specification, such as the data type and nature of the activities, impacts the model size and training speed. So we could say the smaller the window size, the smaller the model, and the faster the training speed. And then the pre-processed data are fed to the deep learning models for classification. Deep learning algorithms are more suitable for complex activity recognition because they automate feature engineering and extraction as one of the most important and challenging tasks in machine learning, and it extracts high-level representation in deep layers. In this study, we experimented 3 deep learning algorithms, including Deep Neural Network, or DNN, Convolutional Neural Network, Long Short-Term Memory, CNN-LSTM, and Convolutional Long Short-Term Memory, or ConvLSTM. And these algorithms are commonly used for activity recognition because of their deep structures for automated feature extractions from raw sensor data. Basically, DNN map inputs to outputs through a sequence of data transformation, or so-called layers. In the learning process of DNN, the value of the parameters or weights of the layers are identified in such a way that the network correctly maps the input data to output data. More deep layers in DNN compared to the traditional neural networks make it more suitable method for building a learning model from a large amount of data where manually extracting feature is too complex or time-consuming for building a successful model. This figure shows the architecture of the deep learning models created in this study. Let's see what steps or layers are included in deep learning techniques. In DNN, different types of layers such as dense, flattened, dropout, and softmax layers can be used. Dense layers are regular neural layers which are densely connected and receive input from the previous layers and send output to the next layers. The input and output are connected by the weights. Flattened layers are used to make multidimensional output linear to pass it to the dense layer when needed. Dropout is a regularization method, which randomly, at a probability, drops some neurons to prevent overfitting the model. Softmax can be used before the output layer to output a probability distribution over the different output classes, which defines the probabilities that the sample belongs to a specific class, which in our case would be active state or inactive state. CNN-LSTM integrates convolutional neural network, or CNN, with long short-term memory network, or LSTM. CNNs are manually adapted for image processing. LSTM is a type of recurrent neural networks, or RNNs, which are used to learn from sequence data, basically a sequence of observation over time, and can address some difficulties of RNN in training a stable model in the CNN-LSTM architecture. CNN performs feature extraction on input data through convolutional layers to learn local patterns, while dense layers learn global patterns. Pooling layers perform downsampling operation to produce the most significant features, and LSTM supports sequence predictions. Data are read sequentially in blocks, and features are extracted from each block. And finally, the extracted features are fed into LSTM for interpretation and predictions. ConvLSTM, which is an extension of fully connected LSTM, that means having convolutional structure for LSTM. In convalescent, an extra connection with the previous memory cells is used to account for the effect of the previous input in the current timestamp. So in the training process, the memory cell can consider the effect of the earliest stages. We implement the proposed method on a demolition project with a hydraulic excavator, and we use a commercial mobile application to collect noise and IMU data. The frequency of data capturing was 8 Hz. It was the highest frequency that the commercial application could run and capture data without crashing. And these figures show a sample of IMU data when the excavator was active and inactive. The accuracy of the model was calculated as a number of correct predictions over the total number of predictions, as you see in this equation. Here we have a few tables. Table 1 shows the accuracy of experimented models for activity recognition. Table 2 shows the utilization ratio based on the output of the activity recognition. And accuracy of the model was calculated by comparing with the actual utilization ratio, which was around 89%, as you see in table 3. The developed model resulted in high accuracy for both activity recognition and productivity measurement. For productivity measurement, DNN model using accelerometer, gyroscope, linear acceleration, and noise level data achieved the highest accuracy, 99.78%. But the variation of the achieved accuracies are insignificant among the model and the input combinations. Less than 1% for activity recognition and less than 3% for productivity measurement. Here we compare our approach with other approaches existing for activity recognition and productivity measurement. An et al. Use accelerometer data for activity classification, Kim et al. Use IMU data for cycle time measurement, and Cheng et al. Use video data for idle time measurement. Comparing our method with this method, our method is computationally less complicated because we use deep learning techniques in which we don't need to do feature extractions manually. Particularly comparing with vision-based method, this method is computationally less expensive, and also regarding the accuracy of the models, our model has high accuracy comparing to existing methods. This study has some limitations that can be addressed in future. In the case study, the excavator activities were limited to demolition tasks. The proposed method can be experimented for other types of excavator activities like excavation and loading. More complex activity recognition with more states required to study more detailed equipment operation efficiency. The application that we use for this study for capturing the data had limitation on the data capture frequency. So the impact of data capture frequency on the accuracy of the models can be experimented in future too. Also, the capability of this method can be further explored by experimenting other types of equipment such as loaders and cranes. So the result of this experiment showed high accuracy of the models, over 96% for activity recognition and over 97% for productivity measurement. The equipment-intensive construction project can benefit from the proposed method by measuring equipment productivity, producing benchmark, and comparing the equipment performance with the benchmarks. Automating this process will assist project managers to identify equipment inefficiencies in near real time. And overall, it can contribute to improve equipment productivity and reducing project time and cost. Thank you so much for your attention. If you have any question about this research, feel free to contact me or corresponding author, Professor Kassem. Email addresses are provided here.